Okay, this video is about energetics in Chem2, and it'll be part one of two videos. The first video I'll look at enthalpy profiles and also calorimetry, and then the second video will be on Hess's law and bond enthalpies. These videos will be a summary really of these four parts of the energetics chapter. Okay, so let's start off with enthalpy profiles first of all, and let's go to the next page. Here we are. Two enthalpy profiles, exo and endothermic. So you need to make sure you can draw both of them. You need to be able to label the activation energy and also the enthalpy change for the reaction. Okay, so this one's exothermic. Okay, so if we have reactants over there and products over here, y-axis energy content, and the x-axis reaction path. Right, so we're basically going to get this kind of shape like that. Make sure you do the curve where it touches the reactants line and it touches the products line. Okay, now you can start to label your graph. Okay, so let's start off. Dashed line at the top of the curve and just there and over here. Right, the height, make sure the arrow is done. Oops. Arrow is done properly, so touching the line here and touching the top of the curve here, that would be the activation energy. And then again from the reactants down to the products, again make sure the arrow goes from exactly from the reactants to exactly where the product line is, and that will be your delta HR. Okay, now if you was to add a catalyst to your reaction mixture, then you know that the catalyst will reduce the activation energy. So let's have a look at the brand new curve this time. Start off at the same place, curve will be slightly lower, end up at the same place there, look. And as you can see now, the activation energy is gone. Activation energy has decreased. Okay, so activation energy is lowered. This is with a catalyst, but you also notice that delta HR does not change. So the heat of the reaction, either heat given out or taken in, is unaffected. Okay, and that covers the exothermic reaction path. All right. I'd like you to have a go at the endothermic one. So reactants there and products there. Do the same again and pause the video, have a go, and then I'll give you the answers. Okay, right, the answers then. You got the curve, dashed line, oops, dashed line, top of the curve, always from the reactants to the top of the curve will be the activation energy. Notice how large the activation energy is now for endothermic reactions. Okay, so endothermic reactions aren't as common as exothermic reactions. You can probably say why, because the activation energies are just so much. Okay, heat of reaction, again the heat of reaction is always done from the reactants to the products. So okay, from the reactants to the products, reactants to the products, and you notice the arrow is up, meaning endothermic. Okay, now if you start a catalyst as before, start from the same place, end up at the same place, and the activation energy has decreased. Right, from there we are, there's the activation energy. It's lowered, although it's still a lot more than an exothermic reaction would be. Right, so there we are. That's the exo and endo reaction profiles. Okay, let's move on to the next bit, which is, where are we? What we're looking at is calorimetry, I think. Calorimetry next. Okay, two types of calorimetry. Either you add one solution to another, for example, an acid and a base. Okay, and then you apply your equation, your formula. So let's look at this one. Imagine you've got an acid, 30 cc's, 0.2 moles per decimeters cubed, to an alkali, 30 centimeters cubed, 0.1 moles per decimeters cubed, for example. Inside here you have a thermometer, so you measure the temperature rise. You have your initial temperature, and then you measure your temperature that it's risen to, the maximum temperature. Subtract the one from the other to give you a delta T, your temperature change. Right, so what would you do? You'd use the formula, okay, Q equals mc delta T, temperature change in kelvins. Mass will be your total volume. In this case, it will be 30 plus 30, so it's going to be 60 grams, times specific heat capacity is always given to you in the question, and it's either 4.18 or 4.2. Temperature change is measured in kelvins, but the change doesn't really matter whether you use degrees C or degrees Kelvin. For example, if temperature 1 was 22 degrees C and your temperature rise was up to 52 degrees C, then delta T equals 30 degrees Kelvin, 30 degrees centigrade, or even 30 degrees Kelvin. Temperature change is the same. So 30, and then you work out your value, and that value will be in joules. Okay, right, next what you got to do is you may want to work out the joules per mole. So you need to work out the moles of each of your solutions. Okay, so let's just work out the value of this first. Okay, so it's 60 times 4.2 times 30, and that comes to 7560. Where are we? 7560, and you could change that to kilojoules now if you wanted to. Just divide by 1000. 1, 2, so it'll be 7.56 kilojoules. Okay, right, let's work out the moles. Sorry, this one here. Let's work out the moles of each of our solutions. N equals CV. Alright, so concentration 0.2 times volume, which has got to be in decimeters cubed. So divide the 30 by 1000. 1, 2, 3, 0.03. 0.03, and that comes to 0.2 times 0.03, that is 6 times 10 to the minus 3, 0.006 moles, and this one N equals C times V, so it's 0.1 times volume, which is 30 divided by 1000. 30 divided by 1000 equals 3 times 10 to the minus 3, so 0.003. Now you got two different types of moles, values for moles, 0.006 and 0.003, and what you would do is you would divide the joules by the smaller moles, because that's the limiting factor. Okay, so Q is equal to little q over N, and that is equal to 7.56 divided by 0.003, and if you do that, 7.56 divided by 0.003 equals 2520. Where are we? 2520, and that is now kilojoules per mole. So that would be how you would calculate the energy of a reaction involving two solutions that you're adding together. Another possible calorimetry type of question would be where you've got a solid added to a solution. For example, here, okay, for example, zinc powder added to copper sulfate solution, and the temperature rises. Okay, notice from here that the reaction is 1 to 1. Okay, now as before, I'm just going to calculate the moles, okay, of the zinc, using this time N equals mass over the molar mass. Okay, so 4 grams divided by, what's zinc? 65. Zinc is 65.4. Right, so that comes to, where are we? 65.4. 65.4, and that comes to approximately, I've got it written down here, look, 0.0615 moles. Okay, and for the copper sulfate, let's just work at the moles. N equals C times V, so it's 0.1 times 50 over 1,000 times 50 over 1,000, which is 0.05. 1, 2, 3, yeah, and that gives us 0.005 moles. Okay, so you've got two different types of moles. See if I can use this. That one. Right, so you got that one. That'll work. Yeah, that many moles and that many moles, and so we know which one to divide by the smaller mole value. Okay, so let's come back to. Let's use that. Right, so work out the energy change. Q equals mc delta T, which is equal to m. Now the m is the mass of the solution. You don't add the mass of the zinc. It's just the 50 times 4.2 times delta T, temperature change. Now, I haven't given you a temperature change here, so I'll say that the temperature rose by 27 degrees, right? C. Okay, so that's going to be the same as 27 degrees Kelvin. Delta T is the same, remember. Okay, so I'm just going to work that out. Say 50 times 4.2 times 27 equals 5670. 5670. Remember, the units are joules. You have to change them to kilojoules yourself. Okay, let's work out big Q, which is little q over N, equals, and I'm going to change that to kilojoules now as well. You don't need to, but you can. 5.67, right, kilojoules divided by the moles, and I'm going to choose that one. No, hold on, yeah, that one there, smaller moles. That's the limiting factor. So in effect, we've got excess of zinc, so which is not all going to react, of course. Therefore, so 0.005 moles, and that comes to, so let's just divide that, 567 divided by 0.005 equals 1134. So we got 1134 kilojoules per mole. Okay, right, so there's another calorimetry type of question. All right, now you may want to account for heat loss. If you come back to this experiment here, right, when you add the zinc to the copper sulfate, temperature is going to rise, but it's not going to rise as much as it should because there is heat loss. It's an open top container, and the thermometer gets warm, the actual cup itself could get warm, so you're losing energy, you're losing heat. So instead of 27 degrees centigrade temperature rise, it should perhaps be 28, 29, 30, 32 degrees centigrade. But we want to know how much it should be. Can we account for the heat loss? Well, yes, we can. Right, so there's your zinc, there's your copper sulfate. You make a table of temperature against time. Okay, you measure for the first 3 or 4 minutes, you measure the temperature in your beaker or your coffee cup. and the temperature stays constant. On the 4th minute, you would add your zinc powder, so you don't take a reading of temperature there. On your 5th minute, you do take a reading. 6th minute, you do take a reading, etc. You notice the temperature rises, and then it starts to fall. Okay, when it starts to fall, carry on recording for a few more minutes and then stop. Okay, then you would take these results and then plot a graph like so. Plot a graph like this, temperature against time, and you're going to get a nice smooth kind of nice little graph like this. Okay, let's see if I can, let's use that. So now I'm going to join my dots up. Now don't join the dots, best straight line through the point, so here. Okay, and I'm going to extend it, extrapolate there, use a ruler of course, and over here, okay, if I get this right, over here I'm going to go, I can do a smooth curve, freehand. Freehand, you could do a lot better than this of course. And then down here you stop, and then over here you would use a ruler to draw a straight line as best as you can. Doesn't have to go through all the points, just the best straight line through the points. Now extrapolate with your ruler. Okay, I haven't got a ruler, but extrapolate with the ruler, straight line. It's not horizontal, as you can see, it's not horizontal, but follow this line up to the y-axis here. Okay, now that point there where it touched the line, and this point here, right, the difference here will be your delta T, which accounts for heat loss. Okay, notice over here, look, that was the maximum temperature rise, wasn't it, before, around about there? That was your 27 degrees. From here to there, that would have been your temperature increase, 27 degrees. But accounting for heat loss, can you see how the extra distance is travelled? And that will give you a better value of Q. Okay, right, so we'll stop the video there, and that'll be part 1, and then part 2 will cover the other 2 bits I mentioned earlier. Okay, let's stop there.